Good morning, everybody. Today is a pleasure to have with us José Luis Ortíz. Most of you know him. He started some years ago at the IAA, and he did a PhD here, and then he went to the as a postdoc to Jet Propulsion Laboratory in USA. Unfortunately for the Institute, he came back and he incorporated in the staff of the IAA in 2000. From there on, he has been working pretty hard with us, and he always teaches us about trans-Neptunian objects, comets, and related matter. So today he will speak about one of the last findings. It's really a very important thing is about the Haumea that most of us heard about this in the newspaper, and today we will learn technically what means this large finding. So when
thank you very much. First of all, I have to apologize because I haven't had much time to prepare this talk properly, and in fact I have to thank Pablo Santos because I borrowed quite a few slides from his recent DPS talk, and sorry about that, but lately I've been very busy. Anyway, I'll try to do my best. The title of this talk is Surprising Characteristics of the Dwarf Planet Haumea from Stellar Occultation. And in fact, this is actually, I'm going to present the findings published in this recent Nature paper, published in Nature on October 12th. As you can see from the large list of co-authors, there was a very wide international collaboration to achieve these findings, and in fact it has been the best ever observed stellar occultation by a trans-Neptunian object. First of all, I have to introduce Haumea quickly. Haumea is a trans-Neptunian object. Trans-Neptunian objects are very interesting bodies. We used to say that they are cool, and in fact, this is the name of a Herschel Key project, which was called TNOs Are Cool. But the truth is, they are not cool, they are very cold. They are typically 40K or so in temperature, so they were appropriate for Herschel to observe them. And trans-Neptunian objects are bodies that, by definition, reside beyond Neptune. Pluto is obviously a trans-Neptunian object, but the first object apart from Pluto ever discovered was 1992 QB1. You can see here the first images of discovery made by Jewett and Liu in 1992. Since then, around 2,500 TNOs are known, have been discovered, but we suspect that they are in the order of 100,000 TNOs of around 100 kilometers in size in the trans-Neptunian region. The trans-Neptunian region extends somewhat to a distance that we cannot really tell right now, but after some few hundreds of astronomical units, there is a transition to the so-called inner orb cloud, and then at around 10,000 AU to 100,000 AU, we have the Oort cloud, which is a spherical cloud, not a belt or a disk, as we know in the trans-Neptunian region. So TNOs are leftovers of the solar system formation, so they carry important information on the process of the solar system formation. So they are very valuable and interesting bodies to observe. And Haumea is not only a trans-Neptunian object, but it's also a dwarf planet. We know that in our solar system, according to the current definition by the IAU, we have 8 planets and 5 dwarf planets. So Haumea is one of the important bodies of the solar system, and it's in the trans-Neptunian region. There are 4 dwarf planets in the trans-Neptunian region, and there is Ceres in the asteroid belt, which is also a dwarf planet. Among the dwarf planets, we knew the dwarf planets really well from either spacecraft visits or through the use of stellar occultations, but Haumea had not been observed through a stellar occultation, so we did not know the basic properties of Haumea like the other dwarf planets. So Haumea was the remaining dwarf planets which had not been properly characterized. So we tried to predict and observe a stellar occultation, because stellar occultations are powerful techniques to determine size, shape, albedo, and a few other characteristics with high accuracy. Of course, it's best to send a spacecraft and measure those properties directly, but apart from that, the best technique that we have available is stellar occultations. Besides, stellar occultations can tell us if an object has an atmosphere, and if it has, it can characterize its temperature and pressure profile. But the thing is, predicting and observing stellar occultations by trans-Neptunian objects is really difficult. It's hard. Why? Because the angular diameters of these bodies are very small. Here you can see a comparison of the angular diameter of Pluto and its moon Charon compared to a few trans-Neptunian objects, and also the angular diameter that an euro coin would have at 140 kilometers from us. So the angular sizes are around 30 milliards seconds, 20 milliards seconds. So these are really small sizes. So we need to know the positions of the stars and the TNOs with that or even better accuracy in order to predict when these occultations will happen. But we don't have catalogs with that stellar catalogs with that accuracy. Although very recently Gaia, the Gaia space mission has provided or is providing data to that level of accuracy, but this is very recently. And the main problem is that the orbits of the TNOs, which are not observed by Gaia is not sensitive enough to record trans-Neptunian objects. So the positions of the TNOs are very uncertain because the orbits are not well known, and typically the uncertainty in the positions are in the order of 400 milliards seconds. So it's a factor of nearly 40 worse than what we need. So so how can we manage to predict and observe stellar occultations? It's difficult. It's a tricky business, and what we do. I'm quickly summarizing this because I would need an entire talk to explain this properly. But what we first do is to select potential or compute potential occultations, and once we have a set of the most promising events, we have to refine those predictions. And in order to refine the predictions, there are many techniques, and we have developed a successful approach by using astrometry, astrometric observations of TNOs, let's say to anchor the orbits and extrapolate the orbits. But there are lots of details, and this is basically the idea. So we use astrometric observations to refine predictions. And for example, this is one of the initial predictions of the occultation by Haumea on January 21st, 2017. We first made the first predictions in 2015 using the URAT-1 stellar catalog, which was not very accurate, nothing comparable to Gaia. And the initial prediction was not favorable for any location on the Earth. This is the expected shadow path. I mean, the path of the shadow that would fall on Earth would be outside any possible region where we could deploy telescopes. So, but this was the initial prediction, and once we had data from Gaia, we improved it a little bit, and it was still not favorable. But then we decided to study the Haumea, to make astrometric observations of Haumea carefully, to try to determine the occultation with more accuracy, which, as I said, the trans-Neptunian objects part is the most important one. Then we decided to do a long campaign of astrometric observations for Haumea. We got more than 1,000 astrometric measurements in a period of more than 100 days, and then we computed the residuals of the astrometric observations compared to an orbit by the JPL horizon system. And you can see, for instance, here the residuals in declination. And from a periodogram analysis, we obtained a period of 49.5 days, which is precisely the orbital period of Hiaka, which is a satellite that we know it's orbiting Haumea. So we could see the oscillation caused in the position of Haumea caused by the satellite. So we had to account for this to make a very accurate prediction. Fortunately, we did this with a small telescope, 0.7 meter telescope that we have in La Ita Observatory in Toledo. But we could replicate this just a couple of months before the occultation with data from several other telescopes. You can see here that the sinusoidal fit, the minimum and the maxima in the residuals correspond to the moments when the Hiaka was at its northernmost position and at its southernmost position. So the residuals were correlated with the position of Hiaka in its orbit. So as I said, we could also replicate this with larger observations from larger telescopes, and I just want to explain quickly that we see this oscillation because the photocenter of Haumea and its satellite, it's slightly offset to the satellite, to Hiaka. So when Hiaka completes a revolution around Haumea, the photocenter also rotates around the center of mass. So that's why we see those oscillations in the astrometry. And in fact, I also have to say that we cannot resolve Hiaka and Haumea separately. In order to do that, you need the Hubble Space Telescope. From the ground, we don't resolve them. So with all these careful analysis, we could at last we could be able to we could make a good prediction in the end, and this was favorable for Europe and a large part of Europe. So as you can see, the shadow path was in the end favorable for a large part of the world. So we made a big campaign. We arranged a big campaign. Of course, we had pre-alerted several colleagues in Central Europe and Italy, and in the end we launched the observations. And also we observed from Spain and several sites in France and also in Turkey, just in case we had made some systematic errors which sometimes are present and we don't know why, but in order to avoid that possibility, we made a very large campaign to maximize the chances of success. So this was the final path on Earth, and these in green you can see the sites from where the observations were successful. In red there are a couple of sites in which no occultation was detected, and in blue we show a site where the ring was detected but not the main body. I will go back to that point later. So in the end the prediction was only around 400 kilometers off compared to the reality. So there were observations from 10 sites and from 12 telescopes. As I said, this was the best observed occultation by a trans-Neptunian object, and it was difficult because the magnitude of the occulted star was 17.8 or something like that, which is similar to the magnitude to the brightness of Haumea itself. So we expected around a 40% drop of the flux of the combined source Haumea plus the star. And the motion of Haumea relative to the star was seen from Earth was 13.1 kilometers per second, so we expected an occultation that would last from tens of seconds to maybe on 100 seconds in the central part. And these are finally the light curves that we obtained from CCD observations. We do photometry of the combined star plus Haumea source, and we get these light curves that we show in what we call normalized flux, which is the flux of the source divided by the flux of the star outside the occultation. So we offset them in steps of 1 to in this plot. So the thing is, most of CCD cameras in most of telescopes don't take are not very fast. Don't take images one after another without interactions. Usually the readout and the saving to disk takes time. So we have some gaps in the data, except for instance at Concoli, where a fast readout CCD camera and EM CCD camera was used, but in the rest of the sites we had interruptions in the image sequences, and this was important, for instance, because we missed the occultation of the egress of the ring occultation in Escalante, but I will explain that later. So as you can see here, there are in the light curves, there are typically a big drop which corresponds to the occultation of the main body, and there are secondary events, brief events, which at the beginning we did not know how to interpret, but in the end we realized that they were the indications that there was a ring around Haumea. Prior to this occultation, the Haumea by the occultation by Maki was the best observed occultation from 5 sites using 7 telescopes. But I will I now get into detail to the secondary events. You can see here these brief and secondary events. When we plot them in the plane of the sky, these are the secondary events from all the observatories. They align with an ellipse. I mean, you can fit an ellipse to them, and which means that we have observed, we have detected a ring around Haumea. At the beginning, we thought it might be a satellite or several satellites, but as you can see, there are so many detections that Haumea would have to be surrounded by lots of satellites, and the fact that they are in an elliptical configuration cannot be explained by anything other than a ring system. So Holar is what? I cannot tell that number, but it's apparent because the ring actually is circular, and the ellipticity, what the ellipticity tells us is the tilt angle of the ring with respect to the observer. So from these observations, we can fit an ellipse, and as I said, the ring has a radius of 2,290 plus minus 60 kilometers, and it has a width of around 70 kilometers. The width, we determine it from a fit to the profile in the light curve with the highest temporal resolution, which was the Concoli one, and so we could fit a profile to that light curve, and so we determined that the width in the ingress at ingress and egress was around 70 kilometers, and we used that for the rest of the sites to compute the exact times when the rings were crossed by the stellar occultation. And also the position angle of the ring is minus 74 degrees, which, as we will see later, agrees with the tilt angle of with the position angle of the body of Haumea, so that makes sense. But now this is related to the question that Emilio just said and just asked, because we know that rings are circular, so since we see it as an ellipse, that means that we're seeing it with a tilt angle. And comparing the semi-axis, the semi-major axis and semi-minor axis, we can determine that tilt angle, which is 13.8 degrees. So it's not edge on, but it's close to edge on, because the edge on configuration would be for 0 degrees. And at 2,290 kilometers, this ring is well within the Roche limit of a fluid-like satellite. So we are confident that no moon can accrete there because of the tidal effect of Haumea. So everything makes sense from a physical point of view, and also we can determine the position of the pole of the ring, and we have two possibilities, because we can see the ring like this or like that. So we had to exclude one of the possibilities, and in fact we used photometry, time series photometry, to discriminate between the two possibilities. Here you can see the absolute magnitude of Haumea from the time of discovery till the present, and of course these measurements have large uncertainties because they are based on archived data from photographic plates, but these ones are accurate. So and you can see different models superimposed for different reflectivities of the ring, together with the shape of Haumea. And we can do the same for the amplitude of the rotational light curve. We can model it. We can model it and include the effect of a ring. And the thing is, only one of the two pole orientations that I mentioned is compatible. The other one gives completely data that do not agree at all with the models that do not agree at all with the data. And also we can see that models with rings which have a contribution in brightness larger than 5% of the total flux of Haumea plus the ring do not fit the data. These are the blue lines here. So we know that the ring cannot be brighter than 5% compared to Haumea itself. So since we know the width of the ring and and its size, its radius, we can determine the albedo of the ring, and it turns out that the albedo of the ring is at least a factor of 5 smaller than the albedo of the surface of Haumea. So the rings are relatively dark, but they are in agreement with the other detected ring in the solar system in a body that is not a planet. Prior to our finding of a ring around Haumea, we had discovered a non-planetary sized body which had rings. This was Chariklo. Chariklo is a centaur. It's a body that is supposed to come from the trans-Neptunian region, and Chariklo is a small body with 250 kilometers in size approximately. And in 2013, we discovered that it had a ring because we saw these secondary events, nice secondary events in the occultation light curve. This is the occultation of the main body, and these are the secondary events in the best light curve. But of course, we had detections from several other sites, so we could conclude that Haumea had a ring. Chariklo had a ring, and this ring had 7 kilometers. This ring system had, in fact, 2 rings, one of 7 kilometers in width, a gap, and another ring with 3 kilometers in width. And the radius of the first ring was 405 kilometers, and the other one was 390 kilometers. So we already knew that there was another body in the solar system that had rings, and also the albedo of the rings of this body turned out to be similar to what we obtained for Haumea. So it's interesting to compare between these two cases, because when we discovered this and published it in 2014, it was not clear if this was a very weird body, a strange body in the solar system that happened to have a ring. But we now think that rings may be far more common than what we thought before. This is an animation that I will skip because, okay. And now I will go now into the details of not the rings, but the body, the main body of Haumea from the occultation data. The thing is, from the chords, from the from the duration of the main occultations in the light curves, we can determine what we call chords in the plane of the sky, and we can fit an ellipse to those chords and determine the size of the projected shape at the time of the occultation. This was 1,704 kilometers and 1,138 kilometers in the other axis. Here I show the 2 axes, but as I said, this was in a specific time when we observed it, and since we know that Haumea is a triaxial ellipsoid, we have to reconstruct the true shape of Haumea, not just the projected one that was observed in the occultation. Also, from the projected area, and given that we know Haumea's brightness accurately, we could determine the geometric albedo of Haumea, which turned out to be around 51%, which is very high, but not as high as it was thought to be, based on thermal measurements, and which are far less accurate than occultation. We had a constraint of around 0.8 or 80% geometric albedo. But the reality is that Haumea is far less reflective, which means that the surface is covered with water ice, as we know, but probably is not, the mixture of ice with rock is not it's not very pure in water ice. Maybe it's a mixture with more rock than we had thought before. Also, as I said, we observed the projected shape at a specific time, and we know from the rotational light curve of Haumea that at the time of the occultation, Haumea was exactly in a minimum of its rotational light curve, which means that we were watching Haumea when its projected shape was minimum. So the true dimensions of Haumea must be much larger than what we derived from the occultation, because we know that the amplitude of the light curve was 0.25 magnitudes. We could in principle determine the true longest axis of Haumea, but I have to say that this amplitude was determined from the ground, and since we have the contamination from the flux of the satellites, we don't observe from the ground the real amplitude. We need to use observations from space, from Hubble Space Telescope, and in fact, those measurements were made, and the true amplitude is 0.32 magnitude. So Haumea, it's even more elongated than one can get from the ground. So if we combine all the constraints, and assuming that the amplitude, assuming that the flux of that we receive from Earth is proportional to the projected area, and knowing the aspect angle or the tilt angle, which we use the one determined for the rings, so we can compute the exact semi-axis of the body, A, B, and C, and it turns out that the dimensions are 2,320 in the longest axis, 1,700 in the intermediate axis, and 1,025 kilometers in the shortest axis, and the equivalent volume is nearly 1,600 kilometers. I should say that in this, to compute this, we did not take into account the contribution of the rings to the flux of Haumea. If that contribution is, let's say, 5%, then the amplitude of the light curve would be even larger than the 0.32 Mach that I explained before. So the longest axis of Haumea can be even longer than this value. But anyway, it's far larger than thought before. From previous thermal measurements and other estimates, it was thought to be around 30% or 20% smaller than that. So here you can see a nice comparison of Haumea and Pluto, and also Chariklo. Here you can see in its longest axis, Haumea is almost as large as Pluto, and the ring system is considerably larger than the ring system in Chariklo. Now, an interesting stuff is the density of Haumea. From the 3D reconstruction, we can determine the volume, and we know the mass of Haumea because the orbit of the satellite is well known. The period is well known, so we can derive the mass using Kepler's equations. So the mass was well known long before the occultation, and using the volume we got a density of 1800, which is much smaller than thought before. Previous estimations for Haumea were in the order of 2,500 kilograms per cubic meter. But of course, this density makes far more sense because it's similar to Pluto's density, and it's more similar to the few other densities that we have been able to measure in the trans-Neptunian region. So it makes smaller density makes sense, but in fact the density could be even slightly smaller than that, because as I said, the longest axis could be somewhat larger if the contribution of the ring to the total brightness of Haumea is more than 5%, which we don't think is the case from the photometry, but we cannot discard it yet. And the thing is, for the rotation period of Haumea, and assuming that it is in hydrostatic equilibrium, we can determine the density of Haumea, and in order to be in hydrostatic equilibrium, Haumea would have to have a density of nearly 2,500 kilograms per cubic meter, which was in the other determination that I mentioned before. So we have a problem here. So Haumea cannot be a homogeneous ellipsoid in hydrostatic equilibrium. So either Haumea is not homogeneous, or it's not in hydrostatic equilibrium. I have to recall here that the definition of dwarf planet is a celestial body that is in orbit around the Sun and has sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes hydrostatic equilibrium. So we have to investigate whether Haumea may have a central concentration, which we think is the case, because we expect that bodies as large as Haumea can be differentiated. But we are not sure that with that will be sufficient, and in fact we think that probably the best explanation for this is that Haumea does not behave like a fluid body, so it behaves more like a granular media, for which granular media can reach equilibrium under rotation for different densities than pure fluids. So this is interesting, and we have to investigate it in the near future. Also, another important aspect from the occultation is that the occultation events of the main body were abrupt, were not gradual, so we can give constraints on an atmosphere, and the result is that the occultation profiles are so abrupt that Haumea does not have a global atmosphere, at least to a level of 15 nanobar if it were dominated by nitrogen, or 50 nanobar if it were dominated by methane. So we can conclude that if a global atmosphere exists in Haumea, it is extremely tenuous. And this is it. So if you have
any comments or questions?
I have a terrible voice. It's better without microphone. Congratulations for very nice work, and I'm surprised about the results and the densities and so on. But what it looks like is you are having, you will need you are about, your volume is 1,800, the density, and the density expected, you said it was something like 2,500, that means a 50% difference. Well, the error in the volume that you obtain is very small. No? In fact, it's very, very small. We are surprised. How can you be so certain about this volume? The errors you have are really small, in the order of 2%. How is this possible? I mean, I believe it's possible, but I don't know. Any comment about that? So how can you be at that certainty level?
Well, the errors in the axis when one makes an occultation are typically in the order of a few kilometers compared to 1,000 something kilometers. The errors are tiny, are very small. So this is why stellar occultations are very important, and we have to pursue them and make them, because we can determine sizes very accurately. It's not like thermophysical modeling of using radiometric techniques. So it's a very accurate way of measuring size. But the thing is, to be honest, in our case, we have to also assume a three-axial shape, and also the contribution of the ring brightness does not constrain very well the long axis of this triaxial body. So the truth is that including that effect, our determination is somewhat less certain. Anyway, it's still very good.
Congratulations. Do you have any guess of the mass in the ring compared with the mass of the planet, of the dwarf planet? Mass. Any comparison between the mass in the ring and versus the mass of the dwarf planet?
Yes, we've made some calculations, but I don't recall them right now. I think it's a tiny fraction. I think it was in the order of 10 to the minus 5. But I don't recall exactly.
The one, if the large axis of the of this Haumea is about the size of Pluto, why does Haumea have a ring and not Pluto?
Question is, why do these bodies have rings? And it's not easy to explain. A possibility is due to collisions, because a collision with the main body can eject a lot of material that can remain in orbit, and if the orbit is if the material is beyond the Rocha limit, it can accrete and form a moon, and we have a moon in Haumea, and the material that is closer in and cannot accrete to form a moon because it's in the Rocha limit, can make a ring. So some sort of collisional mechanism might explain that for Haumea, for instance. But Haumea is also spinning very fast. It rotates in 4 hours. That's the reason why it is so elongated. And so the centrifugal force in the surface is high, and rotational fission or mass sheddings may have, at least in the past, ejected some material which might have evolved to a ring in the region closer to the Rocha limit, and it could have accreted a moon further away.
Any further question?
Really impressive, Jose Luis. I have just curiosity. Was there any chance to detect the occultation of the satellite? Was it far away from the line of sight at that time?
Yeah, it was too far away, and we also computed the shadow path to see if we had a chance to detect it, and it was not possible in this occultation. In other occultations, there might be that possibility, although the size is much smaller and the chances to detect it are smaller. The larger the shadow path, the better the chances of detecting it.
More question or comment, suggestion? Okay, then thanks again, Jose Luis.